Hey everybody, welcome to the Atwood Machine Lab that we've got going on here. Just got all that Atwood machine stuff up on the board, and what we want to do now is utilize it, kind of look at a lab and go through it. So this is the Atwood machine. It's got a pulley. We've got two masses attached via string to one another, coupled system, and what we're going to do is produce mass imbalances between, say, mass number 1 and mass number 2, and measure the acceleration that is produced regarding that mass imbalance, and then compare it to the theoretical expression for the magnitude of the acceleration, which may be a little bit blurry on the board, but it's in the lab too. The difference of the masses multiplied by g divided by the sum of the masses theoretically is the acceleration. Now, I will state that we will get a little bit of disagreement. It shouldn't be very big, but a little bit of disagreement between the measured values and the theoretical expression. There's a couple reasons for that. One of them is we're not considering any friction in the pulleys, though they're very good pulleys. There's still a little bit of friction involved in them that has an impact on the system. We're ignoring air resistance, of course, which is negligible to a good degree. And there may be some slight differences in the masses that aren't accounted for. I'm not going to go through and measure each mass that we go through individually. I've measured them out with the scale, and they're plus or minus, say, 1/2 gram. So fairly minimal, but it could be additive a little bit and produce a slight amount of error in terms of what the mass imbalance actually is and what we're saying it is. But nonetheless, you'll get the idea of how this system works and crunch some stuff out and do some comparative analysis with respect to that of theory, and that'll be that. So we've got 5 different systems we're going to look at, 5 different mass imbalances. We're going to run each of them 3 times. So I've got a little photo gate system right here that ultimately will be able to determine the velocity of this wheel, or really the velocity of these masses as they go up and or down. So the wheel spins at a certain rate. There's a photo gate there, which is a little laser timing system that can figure out exactly how fast this is moving at any given moment in time. And what we're going to get is a graph of that. So there's a little data acquisition thing, the LabQuest systems data acquisition, that will allow us to look at explicitly the change in velocity with respect to time, and we'll get this nice linear type of curve because we're going to get a constant acceleration. So we should get a nice constant slope for the change in velocity with respect to time, or the velocity with respect to time, excuse me. The slope of that curve is the acceleration. So we will extract the acceleration off of this, the data acquisition, and then compare that to the theoretical expression. So I'm going to run this 3 times per, and it's going to be really, really difficult for you to be able to see the actual numbers over here because they're pretty small. So what I'm going to do in between is take a nice little picture of what the screen has so you can see, and that's how you'll get your data. So you'll see it being run, you'll see a picture of the velocity with respect to time, and you'll also see in that picture a linear expression, a linear curve fit that tells us what the slope is. And it's that slope, m, that is equivalent to the acceleration of the system, the magnitude of the acceleration. So let us just do this, shall we? So there's going to be lots of pictures to look at, but I'm going to put this within the whole video, so no sweat there. So what I'm going to do is, notice it's pretty smooth gliding, right? And the masses are the same, 50 grams, 50 grams. We get no acceleration up or down. So what we want to do is follow the lab, and it says, hey, first produce a mass imbalance that is, well, 120 grams on one side and 80 grams total on the other side. So here's another 50 right here. So that would be 100 because the mass hangers are 50, and then here's a 20. So here's 70 plus the 50. That is now 120 grams of mass, or 0.120 kilograms. On this side, I only want 80 grams total. So the 80 grams is, well, here's 50, and then I've got 2 10s right here. Nice little 10s, 10, 10. So that is 70. And then we've got 2 more 5s. 5, 5. So now this one has 80, this one has 120. So we got a nice mass imbalance, and what we ultimately want to do is take some data of this one descending and this one rising up, ascending, and figure out what the acceleration of the system is when you release it from rest, and it moves. So one thing about this, we don't want things swaying side to side, which is hard to get totally out of the system, and we want one to go directly up, the other go directly down within reason. So to do that, really what we have to do is sort of lift this one up, and then we can kind of take this stream. Actually, just take this one. And notice that this one wants to sway back and forth a little bit. We can lift it up and down until it's staying exactly where it wants. And I can hold it in that position, and get this one to stop swaying within reason. And now we're in a position where we could start thinking about letting go of this, but I got to take some data here. So I start the data acquisition, boom, and then I'll let go, stop the system, good. I'll go ahead and stop this from taking data, stop. I will get the graph so we can take a picture of it. I just want to show the velocity graph, and there's the nice little linear portion. I'll zoom into that. Zoom in. So there is the linear portion, and analyze curve fit velocity. Choose the curve fit linear, and it gives me an acceleration of 1.7374, and I will take a picture of this that you will then have. And you'll be able to see, hey, you got a nice straight line for the velocity versus time, and we got a nice correlation coefficient 0.9992, saying, hey, that's really linear over that time interval, and that's it. So there was run number one for this particular part. So now what do we want to do? We want to do it a couple more times because we want this to be reproducible. That is, we should be getting near the same value each time for the acceleration because we're utilizing the same mass imbalance. So there'll be a little bit of difference because I'm not going to be setting this in exactly the same way every time. But nonetheless, we've got this, we've got OK, and we'll go ahead and run it again. So run this, stop it there. Don't only worry about the linear part. Stop it. I'll zoom into that linear part. Graph. Zoom in. And I'll highlight a nice portion. Analyze curve fit velocity. And I'll do a linear curve fit. And I get 1.7437 this time. I'll take another picture. Good. There we go. Nice correlation coefficient. Once again, 0.9999. Yeah, it's very linear. Fantastic. So we'll do this one more time for this mass imbalance so we can see that we're getting fairly consistent results here. So this one's going to go straight up. That one will go straight down within reason. Go ahead and start this again. And 1, 2, 3, go. There we go. Stop it. And go ahead and zoom into this linear part. Highlight a nice portion of it. And analyze curve fit velocity linear. And again, this time I get 1.7595. That's okay. Take a nice picture. And the reason we're getting around the same value. So your job will be take the average value of that and then compare it to the theoretical expression, produce the percent difference, I believe. Follow what it says in the lab. And then what do? We move on to the next one. So this next one is doing the same thing. We just got a different mass imbalance. So I'm going to take 5 grams from one, and I'm going to stick it over on this one. So now this is 125 grams, and this is 75 grams. What should we end up getting? A greater acceleration, right? We've got the same total mass, M1 plus M2, 200 grams, but now we got a different mass imbalance, a larger mass imbalance. So just go ahead and take a look at what happens now. that there. Stop this from rocking. And go ahead and do this. Okay. Get some data here. Ready? 1, 2, 3, go. Stop it. Fantastic. Stop that. Isn't it fun watching me do this? It's like we're lab partners, huh? Hey, lab partner, how you doing today? I'm doing great. We're just getting some data here. Let's go ahead, analyze this curve fit velocity, get ourselves the linear curve fit, and now I get 2.2345. Nope. I'm gonna take a picture of myself. Good. Obviously, we get a greater acceleration, right? It was like 1.75 before, we're getting 2.23. Correlation coefficient, really good. It's linear, so we'll do this 2 more times for this one. Make sure that this is over the pulley because it has fallen off. And go. Stop rocking. All right. Okay. Get some data. Ready, set, go. All right. Stop this. This graph. Zoom in. Do. Highlight curve fit velocity. And get a 2.2125 this time. A little bit less. That's okay though. Oops. Photo. Go. Got a nice picture of it. Good correlation coefficient once again, as we should have. One more time for this one, right? So that one was a little bit less, probably because this was rocking back and forth slightly, but it's hard to get all the way out. Let's just get on with this, right? Yes, yes. All right, so we're gonna go a 1, a 2, a 3. Nice. Stop. Highlight. Ref. Zoom in. Analyze. Curve fit. Velocity. Wow. 2.2286. All right. So, got 2 of them done, 3 more to go. What are we gonna do now? We're gonna take another 5 grams off. This one, move it over here. Same total mass, a larger mass imbalance, and let's just do this, right? All right, so that looks pretty good. That looks pretty good. And let's do okay. Get some data, 1, 2, 3, go. All right. Got our nice little linear portion here. Stop. This, analyze. Velocity. 2.7248. A little bit bigger now. That's great. Right, as it should be. Do this 2 more times here. Fascinating, right? Oof. Watching somebody else do this over and over. It's a lot more fun to do it yourself in the actual in-person lab, but what can we do, right? We do the best that we can, come up with ways to still run these labs and hopefully extract something meaningful out of them. Go ahead, do this again. 1, 2, 3, go. Whoa, it's okay. And stop that. Highlight that. Zoom in. And we get a, this one gave me a different look for it for some reason, but we still got 2.7191. It's weird that it looks different. Just have to live with it. .7191. Got M for the slope. Must have moved something a little bit. That's okay. Oh well. All right. And we got one more time for this one. Whew. Actual lab class here. Starting really soon. Finish this before I gotta go. All right, here we go. 1, 2, 3. Whoosh. Right, we got a nice linear part there. Stop. There. Zoom in. Highlight that. Analyze that. Curve fit that. And make it linear. 2.7283. Sounds good. All about 2.72, 2.73, getting consistent results. Fantastic. Now what are we going to do? I want to throw another 5 grams over, so to do that, I'm going to take 10 grams off this one, take a 10 off this one, put it over here, and I'll add on the additional 5, and put this 5 back over here. So, got ourselves the next round here. All right, so just making sure we got 50, 100, 120, 130, 135. This is 135, and this should be how much? That's right, got 50, 65. All right, so 135, 65 still adds up to be our 200, as it should. And this one 3 times. That looks decent. That's okay. Take some data. 1, 2, 3, go. Whoa, it's zipping now. Quite a bit faster. Stop that. Take a nice look at that. Graph zoom in. Graph analyze. Curve fit. Linear. Now I get a 3.1852. Take a nice picture of that. Increasing as it should. Okay, get ready to take some more data here. All right, let's just do it. So 1, 2, 3, go. Stop, highlight, zoom in. Analyze, curve fit, velocity, and linear. 3.2146. Video. Back to pictures there. 2.2146. Good. One more time for this one. And almost set, huh? Right spot there. Looks decent. And okay. Get our data. 1, 2, 3, go. Fantastic. Nice. And a linear curve fit. 3.1887. There we go. All right. I think we're on the last one here, right? We're going to do 60 grams. Take 5 off this one, stick it on over here. So we got 60 grams here, 140 over here, 20, 20, 50, 50. There we go. And what's going to happen? This one should be going a lot quicker, right? And that will be quite the case, or a lot larger acceleration, let's say. All right, let's stop that. Give this a nice little portion of the graph. Now 3.6169. 6169. Good. Do this one again. So just in general lab work, a lot of times you're doing the same thing over and over, even in doing research, trying to produce, reproduce, make sure you're getting the right correlations with things. Some people think maybe it's a little mundane, it's a little repetitive, and yeah, it is, but lab work's also very gratifying when you come to some larger conclusion, figure something out that nobody's figured out before, stuff like that, pretty cool. Anyways, this is just reaffirming things. It's still fun to mess around with stuff. 1, 2, 3, go. All right. Stop that. Zoom in, I like that. Velocity. Okay, now we get a 3.712. What do we got? We got one more time. I'll just make sure. Get the lab really quick. Jiggling around. All right. And here we go. Ready? 1, 2, 3, go. Oh, wow. That was amazing. Amazing. I agree. All right. Zoom in on that. Highlight that portion. Perfect velocity. And linear. And this time we got a 3.675. A little bit less than we had previous to that. That's okay. Little variation. That's inevitable. Things swinging back and forth a little bit. Let me just make sure that that was all the data that we need. We did 80, 75, 70, 65. Still at 65. 1, 2, 3, 4. And we're supposed to have 5. So, oh, there it is. Huh, that's weird. It wasn't showing for a second. I've got them backwards. Anyways, I'll fix that. That's it. We got all our data. Use the data, do what the lab asks. We'll be going over it, obviously, and that's that. Yay, Atwood. Have a good one.